Hi everyone, my name is Yewon, and in this video, I'll be talking about our work, Amuse, a human AI collaborative songwriting tool with multimodal inspirations. Music creation often draws inspirations from diverse sources. For instance, Mussorgsky's pictures at an exhibition was inspired by visual arts, while Olivia Rodrigo's driver's license originated from her personal diary entries. However, current music AI systems lack support for integrating inspirations into songwriting process. Text-to-audio systems can provide intuitive control through text, but output fully rendered audio that isn't reusable in creative workflows like in DAWs. Conversely, simply music systems provide reusable musical elements such as MIDI data, but can't easily incorporate non-musical inspirations like images or text. This leads to the question, how can we better support songwriters in seamlessly integrating multimodal inspirations into their iterative songwriting processes? To address this challenge, we present Amuse, a songwriting assistant designed to transform multimodal inputs, such as images, text, and audio, into chord progressions that songwriters can directly integrate and refine within their creative workflows. We began with the formative study to understand how songwriters develop songs for inspirations and how AI could enhance this process. The first finding was that musicians drew inspirations from diverse modalities: narratives, visuals, and music. For example, participants cited books they were reading, personal experiences, action movie scenes, and favorite songs as sources of inspiration. Once they got inspirations, they spent a huge amount of time manually translating these ideas into musical elements, often through improvisation or analyzing music. Lastly, participants emphasized that AI-generated suggestions are most valuable when they're both controllable and easily editable. These insights guided our key design goals for Amuse. First, incorporate multimodal inspirations, which are visuals, narratives, and music. Second, transform abstract ideas into concrete musical elements while ensuring that outputs align with users' creative intentions. Lastly, provide modular musical building blocks that can be refined and directly integrated into existing songwriting workflows. Based on the design goals, we develop Amuse. Amuse supports diverse sources of inspiration, which are text, image, and audio, and it is capable of transforming abstract inspirations into current chord progressions, one of the fundamental building blocks of music that can be integrated into songwriting process. Amuse comprises two features, chord generator and chord transcriber. Chord generator processes text and image inputs, extracting relevant musical keywords that user can select and refine. These keywords guide the generation of chord progressions aligned with intended mood or genre. Users can insert these suggestions to their workspace to listen, modify, and build upon them. On the other hand, chord transcriber accepts audio inputs and transcribes them into chord progressions. Once audio is uploaded, users can set the transcription window to extract key and chords for the selected audio segments. The transcribed audio can be played with the corresponding chords highlighted in sync with the playback. Users can click on chords to insert them directly into the music editor. While implementing the keyword generation and chord transcription pipelines were relatively straightforward by using LM prompting and proven chord transcription API, we discovered that turning keywords into musically meaningful chords was challenging. Specifically, we considered three desiderata for keyword-based chord generation. First is diversity, ensuring that users receive a wide range of options. Second is relevance, ensuring the generic chord progressions align with user-provided keywords. Last one is coherence, which ensures that the chord progressions are musically coherent, in other words, follows the real music data distribution. Ideally, we would have a single generated model capable of producing diverse, relevant, and current chord progressions directly conditioned on user-provided keywords. However, we found this direct generation approach was impossible at the time due to the lack of paired keyword chord data for training. Instead, we had access to two complementary sources. First, an LLM capable of generating diverse and relevant, but often musically incoherent chord progressions given keywords, as it was not directly trained on music data. And second, an unpaired dataset of real-world chord progressions. We combined these resources through rejection sampling. Initially, the LLM generates diverse and relevant but noisy keyword conditioned progressions. Then, we train a unimodal chord generation model purely on real-world chord progression data. This model is not conditioned on keywords, therefore irrelevant, but generates coherent chord progressions. Finally, we use rejection sampling to discard non-musical chords generated from LLM, retaining only those chord progressions that closely match real-world distributions. We evaluated our chord generation method in terms of diversity, relevance, and coherence. First, we evaluated whether our method is capable of generating diverse chords using the self-clue score. We compared our prompting method that generates 30 4-bar chord progressions in a single batch with a conventional suggestion method that generates a single suggestion per query. The result shows that our prompting method increased chord diversity compared to the baseline. To evaluate whether our rejection sampling method produces more current and relevant chords, we used two approaches. First, we used Johnson-Shannon divergence that measures the similarity between two distributions. Secondly, we conducted a human listening study to collect human preference of chord progressions generated by each method. We compared three different conditions for the measurements. First is unimodal, which are chords generated using the unimodal chord model. Second is GPT-40, which are chords generated from LLM. The last is our method Amuse, which are rejection-sampled LLM-generated chords. The results show that our chord generation method is capable of producing current chords that are relevant to keywords. First, using Johnson-Shannon divergence, we show that Amuse's chord distributions are closer to real music data distribution. From the listening study, we found that human listeners found Amuse's chords as natural as the chords generated by the unimodal chord model, and the listener preferred Amuse's chords in terms of coherence compared to the chords generated by GPT-40. Lastly, the listener found Amuse's chord more relevant to keywords than the chords generated by unimodal chord model. To understand how songwriters use Amuse in their AI-assisted creative workflow, we conducted a within-subject study where participants wrote an 8-bar chorus in two conditions, baseline and assist. The study was done using HookPad, one of the widely used online songwriting editor. In the baseline condition, participants were allowed to use only Aria, which is an AI songwriting assistant integrated into HookPad, capable of generating melody or chord suggestions based on user-provided music inputs. In the assist condition, participants had access to both Amuse and Aria. In this study, we identified diverse usage patterns of Amuse. The most common approach was kickstarting their songwriting process with multimodal inspiration, where they used Amuse only at the beginning of the songwriting processes. Second was using Amuse midway through the songwriting process, where using it sparked further inspirations, where ideas came midway through the process rather than at the beginning. Lastly, one participant had a unique approach where they outlined the song with lyrical ideas and used the muse to generate chords. From the post-survey in the study, we identified that using a muse offered more agency in the process than songwriting without it. Participants perceived the text and the image inputs of a muse as a communication channel, feeling they can be part of the creative process with the muse. Moreover, participants thought they could explore new musical ideas and freely express their creativity with a muse. However, this increased agency and creativity in the process did not necessarily mean they more enjoyed the process, nor they got better results. From the interview, some participants mentioned that uncontrolled, random outputs from Aria were sometimes eye-opening and serendipitous, resulting in satisfying results. We also find a sense of disconnection between the tools. Given the two different tools, participants seem to form assumptions about one tool's capability based on their experiences with the other, which means they assume that both Aria and Amuse will generate outputs based on both their multimodal inputs and contextual music inputs in the editor. However, in fact, Aria did not have access to multimodal inputs, while Amuse did not have access to the user melodies or chords in the editor. This led to moments of frustrations or thoughts that using both tools is less intuitive than using just one tool. Our findings suggest interesting research avenues for human AI co-creative systems. Acquiring paired multimodal and contextual music data could be necessary for making a system both multimodal and contextual. Also, as participants both enjoyed controlled and random outputs, we could explore how we can balance these output preferences in music creativity support tools. Finally, while our tool supports static context where users compose at a computer, extending AI support to music improvisation could further enhance creative possibilities for musicians. For more information, including sound examples, please check out our project website or our paper. Thank you.